Welcome everyone to our senior design presentation. It's Ashley D. Space Volco. I'm Eric Berger, and that's Scott Boberitz. And this year, we built a humanitarian UAV with the assistance of the Texas chapter of the AIAA Design Build Fly organization.
So here at Western Michigan University, we have a design build fly student-led organization that's been around for over 20 years. And many of us have been on the team for most of our time here at Western. So we wanted to be able to devote as much time to it as we could. So we decided it would be a good opportunity to use it as our senior design project. This also would help us teach underclassmen and other members of the team about aircraft design and manufacturing.
So every year, AIAA gives out a set of rules for each team to follow in which you will design your aircraft around. This year, like we said, it's meant to simulate a humanitarian mission, and we'll be delivering vaccines using our aircraft. We have 4 total missions, 3 flight, 1 ground. Our first flight mission is our deployment mission, which essentially is just being able to take off the runway, perform 3 laps in 5 minutes, and our second is our staging flight, which we will be loading up these 30 milliliter syringes. And same thing, we'll be completing 3 laps around the flight course in 5 minutes. And the final third mission is, of course, the actual vaccine delivery, in which we will be delivering these essentially wooden blocks that are meant to be the vaccine vials, which are equipped with shock sensors. So we'll be flying around the lab, dropping down, and delivering 1 vaccine package. It will take back off, repeat until all of our packages are delivered. And of course, we have our ground mission, which is essentially just a race to see how quickly we can load and unload our cargo missions 2 and 3. We have our, of course, predetermined flight path that I mentioned before. It's going to be the same for every mission. Also, our takeoff distance will be the same for every mission. It is a 25-foot maximum takeoff distance. So if you were to exceed that distance, you have to taxi back to the starting line and try to take off again. As far as our physical restrictions for our aircraft, we had a linear restriction of 8 feet. So that is, can't have over a 8-foot wingspan. Fuselage can't be over 8 feet long. We also have our weight restriction, which is we have to be under 55 pounds due to AMA regulations, which if we got anywhere close to that, we probably wouldn't be flying anyway. And finally, our final restriction is our power storage for our propulsion system. So we're limited to 100 watt-hours total for our propulsion. However, we are still able to have separate energy storage for our other subsystems, such as our delivery mechanism and our servos.
So given that we're going to a competition, obviously the objective is to get the best score. So on this slide, we show that we have the determination and definition of the mission scores on a per mission basis, and our overall score is defined by the sum of them. So in order to best optimize and design our plane, we've determined the impact that each parameter that we can independently vary has on the overall performance. In this case, we are showing how many boxes that we can drop off, how fast we can fly, and then also how many syringes we can carry. These are what we found to be the biggest impactors. The results of the data that we collected for it are shown on the chart here, where each line represents another parameter that we can vary, and the slope of that line indicates the weight in which it carries.
So this is our Gantt chart. This is what we use for our scheduling, see how we can time out our design process. The solid brown and gold lines indicate our planned scheduling, which is based off of previous year's experience. And the darker, thinner black lines show the actual scheduling that occurred during the design process.
All right, so for our conceptual design, for our wing placement, we have the options of high, mid, or low wings, and we chose to do a high wing because we wanted to make sure we had enough space inside the fuselage for any of the cargo that we were carrying, because with a mid or a low wing, spar of the wing would be going through the center of the fuselage or the bottom of it would disrupt the cargo.
For our landing gear configuration, we chose a tricycle design with shock absorbers so that we can easily drop out any of the cargo we need for the missions out of the bottom of the fuselage, as well as the shock absorbers, so we can land quickly and efficiently without damaging anything. For motor configuration, we chose to do twin wing mounted, and initially we planned on putting just one motor on the front of the plane, and we realized doing the math that it would roughly be the same size as the fuselage and would not provide a lot of thrust because of that. So we instead chose to do a twin wing mounted design. And for the fuselage shape, we chose to do a tubular design because our subsystem, which we'll be talking about shortly, is made to fit in a fuselage shape that is tubular, as well as a tube is much more structurally sound than something like a square or rectangular prism is in terms of stress.
So onto our subsystem design, we initially had two competing ideas. So we had to both be able to store in one mission and then store syringes in one mission and then deploy packages in another. So our cargo solution had to be able to efficiently hold both types of cargo, our boxes and our syringes, and be able to deploy the boxes in a timely fashion, all while keeping minimal weight and CG effect issues. So we ended up having to start with a conveyor belt, which would be a moving platform connected to a servo, which when actuated, would pull the entire line of boxes out until one falls out, the bottom port and the bottom of the fuselage, and then we take on the next lap and repeat. We ended up deciding to scrap this design as the amount of CG shift it had it messed with our stability too much for it to be practical, as well as the shape of it, although it was very efficient for our box storage, our syringe storage, given their circular shape, was far less effective, and we weren't able to get as many syringes in as we wanted. Instead, we ended up moving on to this rotary design, in which we have our boxes are able to go in the sides of it, and we're able to actuate it through a servo on the end, which when it rotates to meet the port, the hole in the bottom of the fuselage, our package will release, and we are able to fly into the next lap, in which we turn another partial turn. In addition, when we get to our final subsystems, in which we had to make some edits to meet our final fuselage designs and size constraints, changing some of the patterns, we had to design shock absorbers. In order to maximize our score for mission 3, we have to get out as many packages as possible. Since we can only drop one for each lap, we have to land each time and do it quickly, which means hard. In order to take the load and not damage any of the plane structure or cargo, we had to make a solution that would be able to absorb that shock and distribute it without going through the fuselage and obscuring our module. This was done by creating a 3D printed bracket that is able to flush mount to the outside of the fuselage surface and use the strength of the fuselage to compress the shock absorbers and give us a soft and quick landing.
After all the conceptual designs were finalized, we then had to go into more detailed analysis. We began by analyzing the power-to-weight ratio versus the wing loading for different takeoff distances and cruising speeds. Set a goal of a maximum cruise speed of 100 miles per hour for mission 2 and a takeoff distance just short of that 25-foot limit. This resulted in a wing loading of about 3 pounds per square foot and a power-to-weight ratio of 170 watts per pound. After getting these numbers, we were then able to calculate how much thrust would be required to take off within 25 feet, which came out to be about 16 pounds. After getting that number, we were then able to use that with the power required to size our motor and battery propulsion system. We selected a 33-volt lithium polymer battery. We were then, with that information, able to perform an iterative analysis to further determine physical characteristics such as wingspan, wing area, estimated weight based on previous year's aircraft, and aircraft performance such as lift, drag, and cruise speeds for each mission. So in this graph here, we can see the different cruise speeds for each of the missions. Now, mission 2 is very highly relied on a fast completion of 3 laps. So for that mission, the aircraft will fly at 100% power, which is represented by this gold curve here. That is our thrust available for mission 2. and where it intersects with the blue thrust required or our drag curve, that is our maximum velocity, which comes out to be about 100 miles per hour. Now, mission 3 is more of an endurance mission. We need to be able to fly for the full 10 minutes available to get as many laps and deliveries as possible. To do this, we'll be only flying at about 12% power, which we can see at this lower red line is about 46 miles per hour cruise speed, which should allow us enough time to complete 12 laps within the 10 minutes. Some more performance characteristics such as cruise speeds, stall speeds, drags, and whatnot are shown in this graph here.
So when we got to our detail design phase, we began to consider using composite materials for our main fuselage and body. However, due to the restrictive cost of the materials, we had decided that it was imperative that we verify them prior to purchase. So to do this, we utilized SolidWorks FEA package to get an idea for whether or not we would be reasonably capable to carry all of our weight and perform our flights without damaging the aircraft either on landing or in the air. To achieve this and also include a factor of safety to ensure that even with our inexperience, any missteps along the way in manufacturing, we decided to take all of our loads and put them to the extremes. We overdid the weights and stresses that we were expecting to experience and put them at the most inconvenient spots that they could possibly achieve with our geometric design to see if it would fail even at this extreme case. As you can see on the visual here, our highest stress concentrations are right around the top. It's right where the molding meets the circular fuselage. And even the drop ports don't have as much stress on them. And even at those points, become 2 orders of magnitude lower than the yield strength of the material, which in this case would have been 2 layers carbon fiber. And our end fuselage uses a layer fiberglass, carbon, and then a carbon Kevlar weave, further ensuring that we can be confident that this won't break as a result of in-flight stress.
Another SolidWorks simulation that was done was a flow simulation over the wings to better understand how much lift would be generated from the addition of high lift devices such as flaps. We need to meet this 25-foot takeoff distance with a fairly heavy aircraft, so we had to deploy some sort of high lift device. We did a lot of research on slotted flaps, which create a slot here in between the bottom of the wing and the top of the flap, which accelerates the airflow and keeps it better attached to the flap, making it more efficient than a plane flap. So this flap here is about 25% chord and half span, and the analysis was done at a 10-degree angle of attack and our takeoff speed of 25 miles per hour, which only resulted in about 17 pounds of lift, which was a little less than we were hoping for. So to further analyze the effect of flaps, we wanted to do some real-world testing in wind tunnels. Unfortunately, due to scheduling conflicts, we weren't able to get into the wind tunnel here, so we ended up using our prototype aircraft to test different types of flaps. So we began with the slotted flap shown previously. You can see the complicated 3D printed hinges that give us the nice slot between the wing and the flap. After getting some tests on that flap, we then moved to very large 40% chord plane flaps and conducted some testing with those flaps too to compare the takeoff distance.
So here appears on the right, you can see some lines in the background indicating the distance at which we are taking off. So with no flaps engaged, we got a takeoff distance of about 40 feet. With our slotted flaps, we got a takeoff distance of 16, and with our large 40% chord plane flaps, we got a takeoff distance of about 9 feet. So due to how complicated the manufacturing process is for the slotted flaps and the overall better performance of the plane flaps, we decided that it would be best for us to go simply with the plane flaps. As you can see, there were some issues with the prototype. We experienced a power failure mid-flight, which caused a crash. But not all was lost because we did find areas for improvement with our aircraft. So we decided to increase our wing area. We decided to also change our airfoil from a NACA 1415 to a NACA 6415 airfoil, which is a larger camber, which will provide greater lift. Again, with the large plane flaps, we decided to implement. And we also wanted to implement a overall cleaner design by streamlining some of the surfaces, such as adding coverings to where the servos are mounted and adding cowling over the engine or motor blocks.
Now, as was discussed earlier, we wanted to use composites in the final plane, but due to the expensiveness of composite materials as well as the workability of using them, we wanted to make sure that we use them only on the final plane. So we began this process by 3D printing the molds in sections, and we did not have the benefit of a much larger print bed, which would have been nice, but we still made it work. And we, after they were 3D printed, glued them all together into these shapes over here, and we sanded them down and filled them in with a P17 white resin, which is very similar to Bondo, but like much more specified for this application. After it was sanded out again, so the entire inner surface of the molds were completely smooth now. They were covered in Martel paste number 2 wax to make sure that the composite layups that we're putting in the molds actually separate from the molds instead of bonding to the mold itself. Because in that case, we would have to destroy the mold or risk just damaging the composite in general. Now, our team had not done composites in several years, so we contacted the help or the assistance of a local expert, which was very, very helpful overall. And we began the process by putting a sheet of glossy film down the table and coating it entirely with resin. From this point on, we put the composite over the top of the glossy sheets and then used a series of brushes to dab in the resin into the material itself to make sure that the resin was getting into as much of the fiber as we possibly could. From there, an additional sheet of that glossy film was then put over the top of the material, as you can see over here. From there, the additional resin was then squeezed out to the edges of the glossy film itself. And at this point, we essentially had our own sheet of pre-impregnated carbon fiber material, which allows us to then cut it easily into whatever shape we want, as you can see here, and also get rid of all of these little fibers and strands on the edges. From this point, we put the entire sandwiched material into the mold. At this point, we put the entire sandwich material into the mold and then started removing the glossy film sheets, sort of almost like stickers, and then pushing it into the corners of the mold and cutting any relief cuts we needed to make sure that the entire surface of the mold or of the composite layer is smooth. Afterwards, we added breather material over the top of the entire layout with mold in it, and then put it inside of a vacuum bag over here to make sure that it ended up in the exact shape we wanted it to be. So we were recommended to leave it in the vacuum bag for only about 4 to 5 hours, but we actually ended up doing it overnight just to make sure that the resin actually hardened and was solid. And successfully, after we retrieved each of the different composite layers, because of the glossy film we used at the beginning, we get this fantastic shiny surface here that looks extremely professional and it's very nice.
So the wings are constructed in a different manner. We used a foam block shown in the left picture. It's a very lightweight EPS material. It's about 1 pound per cubic foot. We've done this for years at DBF and it's worked great, so we decided to continue using it. We start by cutting out a airfoil template of plywood and cutting it out of the block with a laser cutter or a hot wire cutter, sorry. And this allows us to get any taper or sweep that we want, and it's pretty quick. We're then able to take that foam core and add in any additional reinforcements. See in the CAD model, we've got 1 carbon tube and a carbon spar that goes the full length of the wing. The tube allows us to conjoin both the wings to the fuselage and allows the motor box plywood construction to be solidly adhered to a carbon tube instead of something just like the foam. After all the internals were completed, 1/16 inch balsa was then epoxied to the entire outer surface of the wing to further aid in resisting bending loads in flight and to provide a smooth, low drag finish.
So in order to avoid any flexure of the fuselage causing a clamping force down on our modules, which would restrict their motion, we ended up putting in laser cut formers that are made out of 1/8 inch plywood. These are in the front glued in place, holding the 2 halves of our fuselage together and to make sure that they can't deform from their circular shape. And the ones in the back are there for support at the mating joint between the tail and the fuselage, which is held together with a press bit, as well as an external loading screw to hold it in place.
So we were able to fit in some real-time flight testing with the new plane. Weather did hold up for a day or two, fortunately for us. This picture up here is a small sample that we took from 1 flight test You see the brown curve is representative of our in-flight speed, and the gold curve is representative of G-forces experienced in flight. Our total takeoff weight with no cargo included ended up being 14.9 pounds, which is a little bit heavier than what we were hoping for, but it's still workable. Our top cruise speed was about 90 miles per hour, but we were able to pull about 5 Gs during a high-speed turn, and we had a takeoff distance of about 13 feet. And with our estimated lift coefficient of 2.5, we estimate that with our plane fully loaded, we should be able to take off in about 23 feet.
Here you'll see in the video, I actually don't follow the plane that much because I was not expecting it to take off that fast. But that just proves how effective our design was in the end.
So in the end, the actual empty weight of the aircraft ended up being about 15 pounds, whereas we had estimated, hoped it would be closer to 12.5 pounds. We think that this variation occurred from our inexperience with composite materials and possibly over-designing some portions of the aircraft. The tail section is definitely heavier than expected, which resulted in quite a tail-heavy plane, which if we had flown in that configuration, would have made the aircraft unstable and probably crash. Another issue was the landing gear initially was too far behind the center of gravity, which made it hard to rotate the nose during takeoff. So after finding these issues, we had come up with some solutions before competition. We decided to unfortunately abandon one of our drop modules and only carry 80 syringes or 8 packages. We also moved the landing gear forward, added some nose ballast weight, and that got us in a stable condition with a decent center of gravity and an actual maximum weight of 19 pounds, which is close to our maximum estimate of 18.5.
Finally, we'd like to thank several people. We'd like to thank Scott from SC Enterprises for his assistance and expertise with composite materials while we're working with that. Professor Rowe for his guidance on the report writing, as well as his use of the UAV lab space. The WMU Sunseeker team, as well as the Formula One team, for their various assistance and advice and usage of tools throughout the entire course of this process. And then finally, the entire AIAA team for their assistance in manufacturing and input on design aspects. So, wish us the best of luck, because we're heading out to tomorrow.
You have 2 minutes for questions and answers. Any questions?
Sorry, can you say that again?
So it was when we were initially designing the plane, the composite was supposed to be more of just a skin, and the internal structure was going to provide the structure. And I think we just ended up using too much wood in the tail structure that was probably unnecessary, and just a little bit extra reinforcements that we don't think ended up needing to be necessary in the end. So just further things that the team learned that hopefully implement next year, not make the same mistakes.
Anybody else?
Any other questions? So can we check the chat room? Is there any question in the chat room?
Say again?
In
In the chat room. Oh.
Okay, there's nothing. That's okay. So any other questions?
Well, thank you guys very much.
Thank you guys very much for coming.
Any questions?